statistics. If you recall, on the very first day, the very first lecture, I discussed the fact that there are two types of statistics: descriptive statistics and inferential statistics. In Chapter 2, we looked at some descriptive statistics in that we were looking at graphs and pictures and ways to describe data, but now we're going to look at values that describe the data. So when we're using Minitab, if you look in your book, you're going to see all these different types of descriptive statistics have formulas, but Minitab's going to do most of them for us. So to find many of the descriptive statistics using Minitab, you're going to go to Statistics, Basic Statistics, Display Descriptive Statistics. Then you're going to select the Statistics button and choose the particular statistics you need. If you need any graphs like histograms or box plots, you select the graph button and it'll produce the graphs for you too. The first type of descriptive statistics we're going to look at are known as measures of center. Now, measures of center are values that represent the center or the middle of the data set. The most common measures of center are the mean, the median, the mode, and the mid-range. So X, we're going to let X stand for the variable, and it's used to represent the individual data values. Sigma notation, the symbol there in front of the X is the uppercase S in the Greek alphabet. It's called sigma, and it means to add all of the values, the X's, in the data set. And we denote this number of values in a sample by lowercase n, and the number of values in the population as uppercase N. The arithmetic mean is, we have two types that we look at. First, the sample mean. The sample mean is denoted by X bar, X with a bar on top, and it's the sum of all the X's in the sample set divided by the number of values in the sample set. And the population mean is denoted by mu. I know it looks like a U with a tail, but it's really the lowercase m in the Greek alphabet, called mu, mu, and it's the sum of all the values in the population divided by the number of values in the population. Give this a chance and try this for a minute. So here we have the heights of 6 basketball players. I want you to find the mean of these heights. So pause the lecture for a minute, get your calculator out, and try to find the mean. Okay, so you added up all the values and you divided by 6, and you should have gotten 79. The median is the next measure of center that we're going to look at. And it's the value that lies in the middle of the data set when the data set's ordered from smallest to largest. Now, if the data set has an odd number of values, for example 5, then the median is the actual middle data value in the ordered data set. For example, if you had 5 data values and you order them from smallest to largest, the third value would be the middle value, such that 2 values were smaller and 2 values were larger. But if you had an even number of entries, then the median is the average of the 2 middle values. For example, if you had 10 values, then you would average the 5th and the 6th value in the ordered data set. So you'd add the 5th value plus the 6th value divided by 2, and that would be the median if you had an even number of entries. Again, this time pause the video and find the median. Okay, so you should have ordered the data set and taken the 3rd and the 4th value in the ordered data set, added them together, divide by, and you would have gotten 78.5 if you did it correctly. The mode, well, the mode is the value that occurs the most frequently. If no entry is repeated, then we say there is no mode. If 2 values occur with the same greatest frequency, then we say the data set is bimodal. And if there's more than two, you can say that it's multimodal, or some statisticians would actually call that, would go back to saying there was no mode. The best thing about the mode, the mean and the median have to be used with quantitative data, but the mode can be used with qualitative data. Really, the only time the mode should be used instead of the mean or the median is when the data is categorical or qualitative. Pause the video and find the mode. All right, you're right, 78, because 78 is repeated twice. The mid-range is the value halfway between the minimum and the maximum values. So to find it, you add the minimum value plus the maximum value and divide by 2. So find the mid-range. Take the smallest value plus the largest value, divide by 2. Pause the video, try it for yourself, and hopefully you got 79. All right, now the round-off rule, this is just a guideline. Usually, you carry one more decimal place than the original data set. So, but sometimes in homework and on exams, I actually specify a particular number of decimal places I want the answer to be displayed as. If you're told differently, then round off to the specified value. Otherwise, carry one more decimal place than the original data set. So if we had 2, 4, 5, and 6, then the mean would be 4.3. If we're looking at the mean at 2.4 and 2.6, it's 2.5, but because we want one more decimal place, we would say 2.50. It's something that we use often in academia. It's where each value, each entry, has a different weight. I don't use a weighted average in my classes, but many teachers do. Many professors that you have probably do, and they give a specified weight to homework, a different weight to exams, a different weight to labs, a different weight for the final exam. So to figure out your grade, you need to add each value times the weight. An example of a weighted mean is also your grade point average. An A is worth 4 quality points, but an A for a 2-hour class would be 4 times 2, as opposed to an A for a 4-hour class, which the weight would be 4 times 4. All right, the next type measure of description that we're going to look at, the next descriptive statistics, are known as measures of variation. These are values that describe how much variation we have in the data set. The first one we're going to look at is known as the range. The range is the difference between the maximum and the minimum values. It is the simplest, it's just the max minus the min. It's the simplest to compute, but the least informative, and it's overly influenced by outliers, because outliers are going to show up in that minimum value or that maximum value. The more common measure of variation is standard deviation and variance. It's very common, in fact, these are the most common measures of variation, and the formula depends on whether you're dealing with a population data set or a sample data set. So, and the variance we're going to see is just the same thing as the standard deviation. The formula for finding it is the same as the standard deviation, except the standard deviation is the square root of the variance. So the standard deviation is the average deviation of the data points from the mean of that data set. So standard deviation is just that average deviation from the mean. We need to find the deviation from the mean. Well, the deviation from the mean is the value minus the mean. Next value minus the mean. So we're going to take each value minus the mean of that data set. We're going to square those values. We're squaring the values because any value that's below the mean is going to give us negative values. Any values above the mean are going to give us positive values. And if you add up all the negative values plus the positive values, you will always get 0. The sum of x minus the mean will always sum to 0. It's the definition of what the mean is. That's why we square it, because when we square a negative number, it becomes positive. So after we square it, we add them up, then we divide by the number of numbers in the population. We call the population variance sigma squared. Now remember, the symbol next to the parenthesis in the numerator of that fraction, I told you a few slides ago that was called sigma. But that's the uppercase S in the Greek alphabet, and this other value that kind of looks like an O with a ponytail is also sigma, but it's the lowercase s in the Greek alphabet. So sigma squared is what we denote the population variance. And remember, just a minute ago I told you the population standard deviation is just the square root of the variance. And we call standard deviation of the population sigma. Then the variance is denoted by s squared, and the standard deviation is denoted by s. These formulas are still value minus the mean, then square each quantity, then add up the individual squared values. But this time, instead of dividing by the number of values, we're dividing by n minus 1. It is a correction factor for the fact that the standard deviation, when you add that up, it doesn't exactly equal the standard deviation. This is a kind of a deep subject, so just kind of take my word for it that we need to divide, if we're dealing with sample, divide by sample size minus 1, and it's a correction factor. Now we say that s squared, the sample variance, is an unbiased estimator of sigma squared, which is the population variance, since values of s squared do not systematically overestimate or underestimate sigma squared, the population variance. Variation is a value that describes the standard deviation relative to the mean. One of the nicest things about the coefficient of variation is the fact that it is unitless, so that you can compare the coefficient of variation between two populations that are measured on different units. So we have the sample and the population. The only difference between them is x bar stands for the sample mean and mu stands for the population mean, but in either case, it's the standard deviation divided by the mean, then times 100 so that it is described as a percent. If your data values follow these percentages, then you also know that it is symmetric and bell-shaped. So if it's symmetric and bell-shaped, you know about 68% will fall within this value, 95 and 99%. If all the data values are about 68% fall within plus or minus 1, about 95 plus or minus 2, and about 99.7 plus or minus 3, then you know the data is bell-shaped and symmetric. So it goes both ways. But if we don't know that, we can use Chebyshev's theorem. Now Chebyshev's theorem is weaker because we don't have the knowledge of symmetry and the bell shape. But Chebyshev says that at least 1 minus 1 over k squared, where k is the number of standard deviations greater than 1. So for example, remember, if we knew the data was symmetric and bell-shaped, we knew that about 95% of the data falls within 2 standard deviations of the mean. Chebyshev says at least 1 minus 1 over 2 squared, which is 1 minus 1 over 4, which is 3/4. So Chebyshev says at least 75% lies within 2 standard deviations. The closer the data set gets to being symmetric and bell-shaped, the closer that 75% gets to 95%. And the same thing holds for 3 standard deviations. About 8/9 of all values lie within 3 standard deviations. But as the data gets closer to being symmetric and bell-shaped, the 8/9 becomes closer and closer to 99.7%. The thing we're going to look at in the measures of description are measures of relative standing and measures of position. The first one we're going to look at is known as the z-score, or a standardized score. The standardized score is denoted by a z, and it's the number of standard deviations that a given value is above or below the mean. So it's the number of standard deviations a given value is above or below the mean. So if z is equal to positive 2.30, then that means that value is 2.3 standard deviations above the mean. If a z value is negative 1.24, then that means that value is 1.24 standard deviations below the mean. And we can deal with the z-score for a sample or a population, and the difference would be whether you're using sample mean or versus population mean, whether you're using sample standard deviation versus population standard deviation. And we normally round z-scores to 2 decimal places. To use standard deviations and z-scores to determine whether a value is usual or unusual. So usual values are going to be values that lie within 2 standard deviations of the mean, which is the same thing of saying z-scores between negative 2 and 2, including the negative 2 and 2. And values are going to be unusual if they are more than 2 standard deviations from the mean. In other words, more than 2 z-scores from the mean, which means a z-score less than negative 2 or greater than 2. Because recall, a z-score is the number of standard deviations from the mean. Next, we're going to look at measures of position that describe how the data value, where an individual data value lies within the data set. Quartiles, deciles, and percentiles, most of you have heard of percentiles, are all measures of position that are generically called fractiles. Now, a quartile is values that divide the data set into 4 roughly equal parts, such that quartile 1 is such that 25% of the data lies below it and 75% of the data lies above that value. Quartile 2 is the same thing as the median, because it's a value such that half the numbers fall below that value and half the numbers fall above that value. And quartile 3 is a value such that 75% of the data lies below quartile 3 and 25% lies above quartile 3. Quartile range is the difference between the third quartile and the first quartile. It is denoted by an IQR, and it's quartile 3 minus quartile 1. Another value, known as the mid quartile, is halfway between quartile 1 and quartile 3, which is computed by quartile 1 plus quartile 3 divided by 2. If the data is symmetric, the mid quartile and quartile 2 should be roughly approximately the same value. But if the data is not symmetric, then these values will be very different. Percentiles are values that we use, and you've seen them often, to describe a position, or let's say your SAT score relative to all the students who took the SAT. So if you scored in the 90th percentile, that does not mean that you scored 90% of the questions right. It means that your score was better than 90% of the other students that took the SAT. Like the quartiles, it partitions the ordered data set into 100 different parts, with each being about 1% of the values in the data set. And we have percentile 1, percentile 2, percentile 3, all the way up to percentile 99. The general term I told you a minute ago was known as fractiles. The percentile of value x, so given a value and you want to find what percentile that value is, you take the number of values less than x, divide by the total number of values, then times 100. If you're looking for the location of what value is percentile 25, then you take 25 divided by 100 times n, the number of values in your sample set. Take the time now to pause the video and look over example 3 and 4 in section 3.3. And after you've done that, then come back to the lecture and I'm going to talk about those two examples. So the examples were the cotinine measures of smokers. So first let's find the first one. Let's find a percentile of a value. Now look at table 3.4 in your textbook, and it's the sorted cotinine measures of smokers. Let's find the percentile for the cotinine level of 198. We count that there are 22 values in that table that are less than 198. So the formula says take 22, the number of values less than that value, divided by the total number of values. There were 40 values in that data set, times 100, and we get 55. So 198 is the 55th percentile. Thus, the value of 198 separates the lower 55% from the upper 45%. You might need to use percentiles is given a percentile, let's find the data value for that percentile. So again, let's go back to table 3.4, the sorted cotinine measures, and let's find the value for the 33rd percentile. So we take 33 divided by 100 times 40, which is the number of values in our data set. That number comes out to 13.2. Follow the flow chart on page 106 in your textbook. And it says, because we have the 0.2, to round up to the next integer. So we count up to the 14th value in the sorted data set. That 14th value is 121. So the 33rd percentile is 121. Now looking at that flow chart, if the value had been just an integer 13, we would have taken the 13th and the 14th values, added them together and divided by 2. But all of that is on that flow chart on page 106. Now let's look at some values that we use to explore the data. And one thing we can use is graphs, or we can use measures of center, or measures of variation, or measures of position to explore the data and see and analyze the data. Some other things. The first one I want to talk about is known as the 5-number summary. The 5 numbers are the minimum, quartile 1, quartile 2, which recall is the median, quartile 3, and the max value. So that kind of tells you a little bit about the spread of the data set. If we want a pictorial representation of the 5-number summary, it is known as the box plot, or sometimes known as a box and whisker plot. So to do that, we're going to draw a box. In the beginning of the box, we're going to usually do it horizontally. It can be done vertically too, but our box, the beginning of our box stands for quartile 1. The end of our box is quartile 3. There's going to be a line segment inside the box, that's quartile 2. Then we have 2 whiskers that come out, and that stands for the max and the min value. Okay, so you can take, you're going to see box plots whenever you look at lab 2. You saw them when you did lab 2, and you also will see them in lab 3. And you can see examples of them in your textbook also. What's known as a modified box plot. These are values that describe outliers using asterisks. So it has the whiskers like a box plot, but in a regular box plot, the end of the whisker is the minimum value and the end of the upper whisker is the maximum value. But with a modified box plot, it sets up the whiskers that are to be inside the fences. The fences are 1.5 times the interquartile range. So you find the interquartile range using Minitab, multiply that with your calculator times 1.5. Take that value and subtract it from quartile 1 to get the lower fence. Take that same value and add it to quartile 3 to find the upper fence. and then any value that lies outside, which means less than the lower fence or greater than the upper fence, we would call an outlier. In fact, you would call it a mild outlier. And if it's more than 3 times the interquartile range, values that fall outside of 3 times the interquartile range, so you do the same thing, 3 times the interquartile range, subtracted from quartile 1, and added to quartile 3, sets up what's known as the upper and lower fences for extreme outliers. Minitab just uses the mild outliers, but some books would talk about extreme outliers, and those are values that are more than 3 times the interquartile range. Chapter 3. Now it's time to go back maybe and look at your book again. This particular chapter has a lot of information in it. Maybe you need to listen to the lecture again, do the assignments in the My Math Lab website, then watch the lecture for Minitab Lab 3, download Minitab Lab 3, complete the lab either by handwriting your answers in or typing your answers in Word. If you typed your answers, just save the document as a Word document and you can upload it to the portal. If you decide to handwrite your answers in, then scan it with a scanner and save it as a PDF and upload it to the portal. Please do not send me pictures with your phone of your labs. I cannot grade them. All right, thank you. Let me know if you have any questions about this material or the Minitab labs.